Hey everybody, Mr. Johnston here, and in this video we're going to do some notes and talk about oxidation states. And for reference in our textbook, this is section 4.9, at least the first part of section 4.9 we'll be covering. So before we get into this, I do want to just talk about the purpose of why oxidation states are important. So the reason that you need to be able to identify oxidation states is so that you can recognize when oxidation reduction reactions occur. And as we talked about, redox reactions are an important category of reactions, and there's several different types of redox reactions. So we want to be able to recognize when that process is happening. A quick reminder that redox reactions involve the transfer of electrons from one reactant to another. When a redox reaction occurs, one or more atoms in the chemical reaction has a change in oxidation state. So this is why we need to be able to identify oxidation states so that we can know if a change in oxidation state has occurred. So in this example, the reaction between hydrogen and chlorine. So when this reaction happens, there is a change in how the electrons are distributed. Really what ends up happening is, since the compound HCl, the chlorine is the more electronegative element, the electrons are much denser around the chlorine atom compared to the hydrogen atom. And so, in a way, it's like the chlorine has gained electrons, whereas the hydrogen has lost electrons, even though it's a covalent bond and they're sharing electrons. It is important to note that oxidation state is a theoretical charge an atom has, imagining if the electrons were assigned to the atom with the greatest attraction for those electrons. And so, it's a little bit different than ionic charge. Ionic charge is an actual transfer of electrons with results in an actual charge, whereas oxidation states, think of it as a theoretical charge that we're kind of accounting for the electrons. So how do we determine oxidation states? And also, oxidation states is sometimes referred to as oxidation number. We're going to go through a set of rules. You will want to write these rules down, and you probably want to commit these rules to memory. These rules are hierarchical. In other words, if you have two rules that conflict with each other, the rule that's higher on the list takes precedence. That's the one that you follow. So here's the first rule. Oxidation state of an atom in a free element is 0. So if we look at my examples over here, on the right, we have the element copper. The oxidation state of the element copper is 0. In this case, you have the element chlorine. Chlorine is a diatomic element. So even though it has that subscript 2, it's still a free element. The oxidation state of each atom of chlorine is 0. The second rule, the oxidation state of a monoatomic ion is equal to its charge. And so again, if we take a look at my examples over here, you have the calcium ion. Now, the calcium ion has a +2 charge, and its oxidation state is +2. And so the ion charge is the same as the oxidation state. And that's true for both cations and, in this case, the anion, chlorine. Chlorine has an oxidation state of -1 because that ion's charge is -1. Third rule, the sum of oxidation states of all atoms in a neutral molecule or a formula unit is 0. So if it's neutral, the sum of the oxidation states must be 0. And take a look at my example here. So we have this compound, water. Water is neutral, no charge. So that means the sum of the oxidation states, the oxidation state of the hydrogen and the oxidation state of the oxygen must add together to be 0. Keep in mind that there are 2 hydrogen atoms, and so whatever the oxidation state of the hydrogen is gets multiplied by 2, and those must add together to be 0. If you have a polyatomic ion, the sum of the oxidation states must equal the charge of the ion. And so this polyatomic ion over here is nitrate. The sum of the oxidation states of the nitrate, since its charge is -1, the sum of the oxidation states must equal -1. So since there's 1 nitrogen times the oxidation state of nitrogen, plus there's 3 oxygens, and the multiplied by the oxidation state of each oxygen adds together to be 0. Fourth rule, in compounds, the metals have positive oxidation states. So a couple of important groups of metals. Group 1A, the alkali metals, always have an oxidation state of +1. If you have an alkali metal, you automatically know its oxidation state is +1. Group 2A, those are the alkaline earth metals, always have an oxidation state of +2. And so those are automatic. If you have those metals in compounds, then you know what their oxidation states are. Rule 5, put that on the next slide here. So in their compounds, nonmetals have assigned oxidation states according to the table shown here. And so if you look at the nonmetals, we have some that are listed. Not every single nonmetal is listed, but for example, if you have the nonmetal fluorine, its oxidation state is -1. The nonmetal hydrogen, its oxidation state is +1. The nonmetal oxygen, its oxidation state is -2. And so on down that list. Group 7A, those are the halogens. Group 6A, those are the elements underneath oxygen. And Group 5A, those are the elements nitrogen and underneath nitrogen. The entries at the top of the table take precedence. So this is hierarchical, meaning if 2 rules conflict, you got to go with the one that's higher. A couple of things to keep in mind when you are assigning oxidation states. So oxidation states generally depend on other elements that are present in the compound. Obviously, we mentioned Group 1A and Group 2A metals. They're always +1 and +2 respectively, but the other elements in the compound, their oxidation states depend on what they are paired with. When assigning oxidation states to elements that are not covered in these rules that we mentioned, for example, carbon, then we have to deduce their oxidation state from the other elements, the other atoms that are in that compound. So remember that rule 3 that said for a neutral compound, the oxidation states are 0. So if we know one element and we know that it must add together to be 0, we can deduce what the oxidation state of the other element is. And we'll look at some examples of this. So on my next slide, I have examples and practice. So let's go through some of these. So we have Cl2. So this is a free element, which means that the oxidation state of each atom in that free element is 0. That's the first rule. Here we have Na+. This is the sodium ion. Since sodium is a monoatomic ion, the oxidation state of Na+ is +1. That's rule 2. The oxidation state of that sodium must be +1. We have this compound Kf. Since the oxidation state of potassium, that's a alkali metal, is +1, that's automatic. The oxidation state of fluorine, that was one of the nonmetals listed in that table, is -1. Also, since it's a neutral compound, the sum of the oxidation states adds up to 0. So the oxidation state of the potassium is +1 and the fluorine is -1. I gotta get my head out of the way for this one. CO2, carbon dioxide. So from that table on rule 5, the oxidation state of oxygen is -2. The oxidation state of the carbon must be figured out from rule 3. Remember that rule 3 says the sum of the oxidation states has to add up to 0. And so if we know that the oxygen's oxidation state is -2, and we know that there are 2 oxygens, this is a total of -4, which means that the carbon, in order for the oxidation states to add up to 0, the carbon must be +4. And so that +4 oxidation state on the carbon, that's how we get the sum of 0 on the neutral compound. So the carbon's +4, the oxygen's -2. Let's take a look at this example. This is the sulfate anion. Sulfate has a -2 charge. So we want to know what the oxidation state of the sulfur and the oxygen in this polyatomic ion is. So again, oxygen has an oxidation state of -2. In order to figure out the oxidation state of the sulfur, we have to use kind of like we did for the carbon dioxide. We have to know that the sum of the oxidation states equals the charge of the ion. And so this one, the charge of the ion is -2. And so the sum of the oxidation states must equal -2. As we said, oxygen is -2. There are 4 oxygen atoms, so in your head, if you figure 4 times -2, that's a total of -8. In order for us to get a total of -2, the sulfur has to be +6. So the sulfur has an oxidation state of +6, while the oxygen has an oxidation state of -2. That's where we get the charge of the polyatomic ion. Take a look at one more example, K2O2. Remember, potassium, that's an alkali metal, always has an oxidation state of +1. Ordinarily, we would expect oxygen to be -2, but since Rule 4 takes precedence over Rule 5, we're going to remember that the sum of the oxidation states is 0. So if we know potassium has to be +1, then in order for the sum to be 0, if potassium is +1, for that sum to be 0, oxygen's oxidation state in this case must be -1. And so we have those oxidation state. Potassium is +1, and oxygen is -1. For additional practice here, I would like you to go to this website, and I gave you the short URL. You can type in bit.ly/oxstate, and you'll get to some practice. There's some tutorials where you'll read through and take a look at some more examples, and then there's a few to try on your own. As always, if you have questions, please ask. Otherwise, good luck with oxidation states.